So as I mentioned earlier, Dalton wasn't completely correct when he said that all atoms of the same element have the same mass, because there are isotopes. So different atoms, say of chlorine, have different masses, but we are rarely dealing with single atoms. We're usually dealing with a large number of them, and so then we're more concerned with the average mass. So we calculate an average mass. It's called the atomic mass for each element. That is also listed on the periodic table. That's that messy number underneath the element symbol. So here for chlorine, 35.45. That is the average mass of a chlorine atom. There's no chlorine atom that actually weighs that. It's the average of the ones that exist. Instead of a simple average where you measure the mass of each thing and then add it all up and divide by the number, we use what's called a weighted average based on the natural abundance, because these things are too small to count and too many to count, because it would take you your lifetime and beyond. So looking at chlorine. So naturally occurring chlorine, 75.77% of it is chlorine 35 atoms, and 24.23% is chlorine 37. And here are the observed masses. Chlorine 37 has a mass of 36.97 atomic mass units. That's going to be, the atomic mass of an isotope will be very close to its mass number, but not exactly the same, and the reason is complicated. Here's chlorine 35. Its mass is very close to 35. If there were equal numbers of chlorine 35 and chlorine 37 atoms, we could just add those two numbers together and divide by 2 and find the average mass. But there are not equal numbers. There are a lot more chlorine 35 atoms than chlorine 37 atoms. So the average mass needs to be closer to the mass of the chlorine 35. So to calculate an average atomic mass, you take this percentage and convert it into a fraction, the decimal form, just by dividing by 100. So 75.77% corresponds to 0.7577. And then you multiply that by the mass of that isotope, and you get a number. Chlorine 37, there's 24.23%, so we convert that to the decimal form, 0.2423, multiply by the atomic mass. We get a number. Add those together, and that'll give us the average atomic mass. We don't have to divide by anything because that's already taken care of over here. So in fancy math notation, which is often confusing, it's the sum of the fraction of isotope M times the mass of isotope N for however many isotopes there are. So let's do an example. Magnesium has 3 naturally occurring isotopes, masses of 23.99 AMU and 24.99 AMU and 25.98 AMU, and natural abundances of 78.99%, 10%, and 11.01% respectively. Now that word respectively means that we're listing the percents in the same order as the masses, and so the first mass goes with the first percentage. Calculate the atomic mass of magnesium. So I want to take the first percentage and convert it into a decimal. So 78.99% becomes 0.7899. And I'm going to multiply that by the mass of that isotope, 23.99 AMU. I'm just going to write this down and I'll get my calculator out. The next one, how do I make 10% into a decimal? 0.1000. And multiply by the mass. This was the second percentage, so I'm going to multiply by the second mass. And then the third one, 0.1101 multiplied by 25.98 atomic mass units. So now I'm just going to use my calculator, 0.7899 times 23.99. Let's just practice our significant figures. I'm multiplying here. So am I looking at fewest decimal places or fewest sig figs? Sig figs. So here I've got 4 sig figs and 4 sig figs, so that tells me that this result would have 4 significant figures. I'm going to underline the 4th digit. This would have a unit AMU. Do the second one. I'm going to end up with 2.499 AMU. Again, 4 significant figures, 4 significant figures, 4 significant figures. And then that last one, 0.1101 times 25.98. Calculator gives me 2.860398. That also should have 4 significant figures. So 1, 2, 3, 4. To find the average atomic mass of magnesium, we have to add these together. That's what my calculator is giving me. Atomic mass units. How many significant figures? Well, what are we doing? We're adding. So when we're adding, we're comparing fewest decimal places. 2 decimal places, 3 decimal places, 3 decimal places. 2 is the smallest, so our answer should have 2 decimal places. And so we should round that to 24.31 atomic mass units. What's it say on the periodic table? This one says 24.3051. Does that round to 24.31? Yes, it does. Any questions? I'm not going to make you consider significant figures when we do these sorts of calculations, okay? I just don't really see the point. I did this here just to help reinforce what we learned in Chapter 1. But what we end up with typically is the number of significant figures in the percentage or the atomic masses, whichever is smaller. And that's going to be close enough for these calculations. So anyone curious how we find the mass of an atom when it's too small to even see? Yeah. There are different ways. A more high-tech way is called mass spectrometry. And we actually have an instrument that will do this in the room next door, in the instrument room. It's really neat. So mass spectrometry allows us to measure the masses of atoms and, more importantly for this discussion, the percent abundance of those isotopes. And it does this by separating particles according to their mass. So here's an example of what you might get by looking at the isotopes of chlorine. It's going to tell you that if chlorine-35 has 100% intensity, then chlorine-37 has something in here, like maybe 35% intensity. And from that, we can calculate the percent abundance. How does it work? Just a very quick overview here. You're going to take your sample and put it into the instrument. There's a heater here that's going to vaporize it. You can make even metals into a gas. We're going to pass it through here where an electron beam is going to ionize it. So now we're going to have negative particles, and that we do that because that's going to help us be able to make it move, because we can use electrical fields here to cause those ions to move in a straight line at a rapid speed. Adding an electron or two to the atoms does not significantly change its mass, so that's not really an issue. So we send that through here, and then the magnetic field will separate those particles based on the ratio of mass to charge. And so the lightest particles will get deflected the most, and the heaviest particles will get deflected the least. And so by measuring the intensity of the signal at the different positions on the detector, we can get that information. Any questions? You will not be tested on this diagram.